Dear students, this is my fourth lecture on adsorption and probably the last lecture on this chapter, because there is a branch of this chapter which is the heterogeneous equilibria, but there is a minor difference with this. So from that perspective, this is the last lecture on adsorption, and if situation demands in future, then I will definitely deliver lectures on heterogeneous equilibria also. So as a part of last lecture of this chapter, we are going to discuss the BET adsorption isotherm today, which is after the name of Brunauer, Emmett and Taylor, who have formulated the isotherm. So before, actually this is the extension of the Langmuir adsorption isotherm. So before going to the extension, we have to understand the shortcomings of the Langmuir isotherm. That means what were the drawbacks or the shortcomings in Langmuir's isotherm, where Langmuir made some assumptions. So what did Langmuir assume? He assumed that the adsorbed gas only forms a monolayer. So that must be a drawback, because sometimes multilayer adsorption also occur. Next, the surface, he assumed the surface to be uniform, but the surface sometimes is not uniform. Sometimes adsorption takes place in the pores, even in the capillaries of the adsorbent surface. So from that perspective, this is also another drawback. Thirdly, the adsorbent and the adsorbent does not react chemically. Actually, what was assumed by Langmuir was that the particles, the adsorbate particles, do not interact with each other. They behave ideally. But here, chemical reaction may also take place. That means they interact with each other. So this is another shortcoming of the Langmuir assumption. And finally, there is a stable equilibrium between the adsorbate molecule with the monolayer. But actually what happens is there is a dynamic equilibrium among the different layers also take place. That is, a steady state is obtained, not a stable equilibrium. So from those shortcomings of the Langmuir assumptions, the assumptions made by Brunauer, Emmett and Taylor were they proposed, number one, formation of multilayer during adsorption. That means more than the monolayer. Beside the monolayer, some more layers are formed. Secondly, after formation of a monolayer, the adsorbate molecules may condense on it. That means when multilayer formation is taking place, so that phenomena is actually the condensation of the adsorbate gas molecules. As I have said, there is a dynamic equilibrium between the adsorbate molecules in the successive layers. And finally, enthalpy of adsorption is important here. So there are two types of enthalpy of adsorption. One is the enthalpy of adsorption for the first layer, and the second was the enthalpy of adsorption in the other layers. Actually, the first layer is due to adsorption, but the enthalpy, that means the heat released in the other layers, that is the above layers, are actually due to condensation of the gas molecules. So let us illustrate here. Here, this is the monolayer. So this is layer 1. But above the layer 1, there second layer may also form, and some bare sites also left vacant. These sites are left vacant. They are bare. Even on the second layer, the third layer may also form, and so on. So this is the overall picture. Now the monolayer has some certain volume. The volume of the gas in the monolayer, it is actually taken to be Vm, while the overall adsorbed gas molecule has volume V. So these two parameters are important in the BET isotherm. Let us check what is the equation. In the equation, the P by Y part is this one. Okay, actually this is the extension of the Langmuir isotherm, so it will look like the Langmuir isotherm, but there are some more parameters incorporated. So here P0 minus P term has come. This is the difference between the pressure and the saturated vapor pressure. P0 is the saturated vapor pressure of the adsorbent gas molecules, and this P is the current pressure, that means the pressure on which the experiment is going on, and V is the volume, overall volume of the adsorbed gas molecule. That means in this picture the overall volume of the adsorbed gas molecules, that means the molecules in the first layer, molecules in the second layer, the molecules in the third layer, and if so in the other layers also. This volume is actually V. And what is Vm? Vm is the volume only for the gas molecules which are adsorbed on the first layer. So this is the Vm, and this is a constant. Okay, and in the intercept part, y equal to mx plus c, in the c part they have written 1 by Vm into c. C is a constant which is known as the BET constant, and it is a function of the enthalpy of the adsorption in the monolayer, as well as the enthalpy of adsorption due to condensation. We shall see it later. So this is the overall equation. So if this part P by V into P0 minus P is plotted against P by P0, then a straight line with an intercept and some slope will be obtained, where the value of the intercept would be this one and the slope would be this one. So let us check. V is the volume of the gas adsorbed under pressure P. P0 is the saturated vapor pressure of the gas, and Vm is very important. Vm, volume of the gas adsorbed in the monolayer. This is important because this parameter is utilized in future in calculating the surface area of the adsorbent solid. That means on which adsorption is taking place. So the surface area where the adsorption is taking place, that can also be determined with the help of the this parameter Vm. So this is important from that perspective. And as I have said, C is a function of enthalpy of adsorption in the monolayer as well as in the overall adsorbent surface. So C is actually exponential E1 minus EL by RT, which is known as the overall BET constant, but for a particular given or for a given adsorbent, where E1 is the enthalpy of adsorption in the first layer, okay, and EL is the enthalpy of liquefaction of the gas. As I've said that in the second layer, third layer, all these are actually the condensation, that means liquefaction of the gas molecule, the process of the liquefaction of the gas molecule. So these two enthalpies are different things. So this E1 is only adsorption and this EL is condensation or liquefaction. So we have to plot this P by P into P0 minus P against P by P0, then intercept, and this slope will be obtained. Let us see. So this is the graphical presentation, and from this the value of C and Vm can be derived. Now BET successfully explains all the adsorption isotherms. At the beginning of the chapter we have seen that there are 5 types of adsorption isotherms, and from the BET adsorption isotherm or the equation, all the 5 types of adsorptions have been explained well. So these are the pictures. I reproduce them here again. These are all the different 5 types of adsorption isotherms, out of which the first one, we are quite familiar with the first one. This is also explained by the Langmuir and Freundlich isotherm, but this had been unexplained. So let us see how these are now explained by means of the BET equation. Case 1. Case 1 is if adsorption is taking place by forming only a monolayer, that means multilayer adsorption is not taking place, then the above BET equation takes the form of the Langmuir isotherm, because here V becomes Vm, and this Vm cancels this Vm and this Vm as well. So this becomes P by P0 minus P. This way the Langmuir adsorption isotherm is well explained by the BET adsorption isotherm. So if adsorption is taking place by forming only a monolayer, then the above BET equation takes the form of the Langmuir isotherm, resulting in the isotherm of type 1. So this is the isotherm type 1. This is the saturated vapor pressure. Now case 2. In case 2, if E1 is greater than EL, that means enthalpy of adsorption in the first layer is very high, whereas the enthalpy of condensation or the energy released due to condensation is comparatively low, then the adsorption phenomena predominates over condensation at low pressures. But at high pressure, the after this point, after crossing this point, above this pressure particular, it has some value, the condensation process starts to take place, because at that moment the pressure becomes very high. Okay, so up to this point it follows the Langmuir adsorption isotherm, where the curve is something like this, logarithmic curve. But after that, condensation process takes place until the saturation vapor pressure is reached. So if E1 is greater than EL, then this type 2 adsorption isotherm can be obtained. And in case of case 3, the reverse thing takes place, where adsorption in the monolayer does not predominate. Only the condensation process predominates, or that means condensation on the solid surface. Okay, so this type of exponential curve is obtained. This is type 3. Case 4 and 5. In case 4 and 5, as I have said, that the surface in the BET isotherm is not uniform. That means adsorption takes place other than the adsorption sites. Okay, and these other portions of the solid surface where adsorption takes place are the pores and the capillaries of the solid, adsorbent solid. So in the pores and the capillaries also, those adsorbate molecules enter, and this is also regarded as the part of adsorption. So in this under this criteria, 4 and 5 is obtained, and the 4 is obtained when E1 is greater than EL, and 5 is obtained when EL is greater than E1. Okay, so besides formation of multilayer, if adsorption is also taking place in the pores and capillaries, then adsorption isotherm of type 4 and type 5 will be obtained. If E1 is greater than EL, then adsorption isotherm of type 4 is obtained, and if EL is greater than E1, then adsorption isotherm of type 5 is obtained. Now, with the help of the BET adsorption isotherm, as I have said, the surface area of the adsorbent is also obtained. How? The BET adsorption isotherm can be used in calculating the surface area. It is done by determining the volume of the gas required to form only a monolayer. Look at this point. This point. Here, up to this monolayer is formed. After this, that condensation starts taking place. So this volume is actually the Vm. Okay, and this P0 pressure is actually the pressure at STP, and T0 is the temperature at STP. This is not pressure, this pressure. This P0 is not this P0. Okay, this is actually the pressure in the STP, and T0 is the temperature in the STP. Okay, so when the this point, this dotted point shown by the arrow, okay, is reached, then monolayer formation is complete. At that point, the volume of the adsorbed gas would be Vm at STP. So the temperature and pressure are P0 and T0. That means the standard temperature and pressure, where the volume is calculated to be Vm. Now at STP, we have to apply the ideal gas equation, P0 Vm nR T0. N is the number of molecules, number of moles. Okay, Therefore, the number of moles of the gas adsorbed, N equal to P0 Vm by RT0. And the number of molecules of the gas adsorbed, just this is the number of mole. So if it is multiplied with the Avogadro number, then the overall number of molecules is obtained. Okay, so this is the overall number of molecules, gas molecules. Actually this should be N dash, not N. This should be N dash, otherwise these two N are same, no? So this N should be actually N dash. This may be regarded as a typing error. You just put it here N dash. I repeat, you just put it here N dash, not N. You have to differentiate with this N. Now what is the equation for the surface area? If beta is the surface area occupied by a single gas molecule, that means a single gas molecule occupies some area which is beta. Okay, then there are total this number of gas molecules. So overall surface area is what? Is beta into this. Now how do you calculate the value of beta? Beta can be calculated from the density of the liquefied gas, which is D. What is density of the liquefied gas? The density, that means this is the density of the gas at the boiling point. Isn't that? The liquid is condensing to form, the gas is condensing to form the liquid. So the reverse, in the reverse way, we can take it as if the liquid is boiling and it becomes its corresponding vapor. So condensation means the density at boiling point. And if m is the molecular weight, then volume of 1 mole absorbed gas is m by d. M molecular weight and d is the density of the liquefied gas, then m by d is the volume of the adsorbed gas. And volume of 1 molecule divided by N0. Naturally this is for overall volume of N0, number of gas molecules. So if we divide this by N0, Avogadro number, then for 1 molecule the volume is obtained. And therefore what is the value of beta? Beta, if this is the volume, then to the power 1/3 is the side length, and the square of the side length is the surface area. So it is 2 by 3. So this way beta can be calculated. Then put the value of beta in the equation of S in the earlier slide, then you can easily calculate the surface area. So that's all about the BET adsorption isotherm, and that's all about the chapter adsorption. And thank you all.